So, good morning, everyone. So, today, as was mentioned, I'm going to talk about geospatial innovation in action, focusing on the role of mobile mapping, artificial intelligence, and digital twins for informed decision support. So, right now, geospatial data in general plays an important role in several applications, whether it's transportation, resource management, energy, and geospatial data allows us to produce dynamic digital twins, which are very, very important for well-informed decision making. And if you combine these with AI tools, we can ensure the resilience of our infrastructure. So just a quick introduction. So by resilience, we are trying to say that our system can absorb, adapt, and recover from disruptions while maintaining its essential functionality. Digital twin, we are talking about a dynamic virtual replica of the physical systems that includes data, models, and allows also simulations and what if scenarios. So through digital twins, we can enable continuous monitoring and predictive analytics and scenario testing, and we can do better decision making and proactive resilience strategies. So if you look into digital twinning, the 3D modeling of the ecosystem we are dealing with, that's really the main functionality or the backbone of the digital twin generation process. So to allow for this digital twin generation, we need to rely on multi-platform geospatial data integration for the 3D modeling of the ecosystem we are dealing with. And this is deals with several aspects. First, we have to rely on several platforms for the collection of the data. Those could be spaceborne, airborne, UEVs, vehicle mounted, wearable systems like the backpack, robotic systems like uncrewed ground vehicles. And we need this for what we call a scalable data collection. So we would like to collect data, fine resolution data at a scale. Then on top of these platforms, you have to integrate sensors for acquiring information about the environment. That could be in the form of LiDAR or light detection and ranging. Cameras, those cameras could be RGB cameras, multispectral cameras, hyperspectral cameras, thermal sensing. And this will give us geospatial data with high spatial or geometric and spectral resolution. Very important for digital twins that they have to be dynamic. It means that the digital twin is being frequently updated. So to update the information at the right location, we have to have very accurate georeferencing. This georeferencing can be in areas where we have accessibility to GNSS, aided by INS. And in GPS challenging environments, we have to rely on simultaneous localization and mapping strategies or trajectory enhancement and mapping strategies to ensure that the geospatial data we collect from different sensors, from different platforms at different times are properly located in the right position. And then we have to use this multimodal, whether it's imagery, multispectral, hyperspectral, thermal, point cloud. We have to make sure that we can fuse data from all these sensors on different platforms that could be aerial, terrestrial, and in order to generate a comprehensive and complete digital twin. Another thing that we have to focus on is the environmental adaptability. So, meaning that the data acquisition and the data processing strategies should be capable of handling different environments. whether, for example, we are dealing with transportation, urban, agriculture, forestry, shorelines, and so forth. So just to give you some examples of the data acquisition platforms that we are dealing with. So we have spaceborne systems, we have airborne systems. The airborne systems can be in different categories. We have high altitude airborne, medium altitude airborne. And now with medium altitude airborne, we have crewed and uncrewed vehicles. And we can even reach what we call near proximal systems. So these are UAVs or unmanned aerial vehicles or systems that are flying maybe in the from 100 to 400 feet above ground. So these are just examples of these UAVs. And you can have what we call proximal, so you are very, very close platforms to the environment that you would like to map. That could be in the form of tripod mounted systems. You have wheeled vehicles, like uncrewed wheeled vehicles or robotics, wearable systems, whether they are on pedestrian or bike system. And even we can rely on smartphones as the way we collect the geospatial data. So, like here, I am highlighting some of these platforms in red, and those are mobile mapping systems that, and applications we developed at Purdue University. So, on top of these or on board these platforms, you can have different sensors like imaging, as I mentioned, RGB cameras, multispectral cameras, hyperspectral cameras, LiDAR units. You see here several examples of LiDAR sensors. And for position INS integrated systems, like what you see at the bottom here. So these are just some examples of the UEV systems that have been developed at Purdue. So this is a system that's mounted on a DJI M600. It integrates a LiDAR sensor, integrated GPS INS unit here in behind this black cover. We have a hyperspectral in the visible near infrared, and we have an RGB camera. So this is basically, we are looking under the cover to highlight the GPS INS unit implemented on this uncrewed aerial vehicle. You can have a similar payload on a wheeled mobile mapping system. So again, this includes 4 LiDAR units at the 4 corners of the car, 3 digital cameras, and an integrated GPS INS system. This is another example of a wheeled vehicle or mobile mapping systems. Here, it's similar to the previous one. The main difference here that we have higher accuracy requirements, so we have higher end or professional grade or navigation grade sensors. You can have similar architecture. So basically, you have a camera, LiDAR, and GPS INS on a wearable backpack mapping systems. You can have these wearable backpack systems on an e-bike or a regular bike. So we call this wearable bike. You can even take this backpack unit and you can mount it on a car or a truck. So we have what we call mobile pack mapping systems. You can take the backpack and mount it on an ATV. So this is another way of doing mobile pack mapping systems. You can have a similar configuration, again, camera, GPS INS LiDAR unit on an uncrewed ground vehicle or robotic system. And right now we are building medium altitude airborne mapping systems where we integrate larger, more powerful, higher resolution sensors that include LiDAR, RGB, hyperspectral camera, and high-end navigation, GPS INS navigation. And the most important thing about this medium altitude airborne system is that we have an increased area coverage, that we can cover larger area that we cannot cover with the UEV and the backpack or wheeled systems. So this will allow us to do regional deployment. So just to give you an idea about that, these like the technology, whether they are platforms or the sensing technology, they are witnessing uh, quite frequent development. So this is the system. This is what we had almost like 3 or 4 years ago. And then we have been developing the systems. Now we have the NAP XP1 and the NAP XP2 that's just developed, this NAP XP2 that's just developed earlier this year. So one of the key things here I would like to emphasize is that the platform and the sensing technology are witnessing continuous development, and this is allowing us to have more data acquisition at different scales or different resolution. So this is just like the most recent backpack unit. We see here the camera, you have the LiDAR, and the GPS INS unit is in this under this cover here. This is just more detailed view where you can see the LiDAR. This is the GPS INS unit. You have an electronics box here that has a computer, and you have the RGB cameras. And the whole unit is powered by M18 regular tool battery adapter. So this is one of the nice things about this NAP XP2 is that it allows you to do mounting on a backpack. So you have the sensor module, you have the electronics, and you have this mast for the backpack. If you would like to use this system in a UEV system, you remove the mast, and this is how you integrate system on a UEV. You can even integrate this NAP XP2 on a UGV or uncrewed ground vehicle. So just a summary, how are these sensors or systems or platforms are different from each other? So if you look at space-borne systems, we have very large area coverage, and we have lots of legacy data or historical data available. These are the pros. The problem with these space-borne systems is just because of the large sensor to object distance. We have low resolution. We can get high resolution imagery from imaging satellites, but those are usually expensive. When we go to airborne systems, we have large spatial coverage that's still possible. We have also a huge amount of legacy data available. We can capture multispectral, hyperspectral data when we deal with imagery. And for LiDAR also, it's quite possible to have LiDAR data from airborne platform. The main problem with the airborne system is the deployment cost, and also whenever we use imagery or we rely on the lighting conditions, and the cloud coverage could impact the quality of the data we acquire. When you go a little bit closer to the object, when we talk about uncrewed aerial vehicles, the ease of deployment is a big plus because of the small or distance between the object and the sensor. We have higher resolution. The equipment are not really that expensive. We can have imagery and LiDAR data. And the main problem with uncrewed aerial vehicles is that the battery life will limit the duration of the flight to less than 40 minutes, for example. The logistics for flying drones could be complicated depending on where you operate the system and the proximity, for example, to urban canyons or airports. Whenever we use imagery, again, we are impacted by the lighting and weather conditions. And for LiDAR sensors, they are a little bit more expensive when you compare them to imagery. And then we have at the other extreme, we have the terrestrial platforms. So we have very high level of detail, very fine resolution, but it could be expensive, especially if you are targeting deployment in larger areas. And this is mainly you can only do the mapping where you can have the platform access or maneuver within your site. So this is, I usually try to contrast these different sensing platforms from the space, the airborne, the near proximal, and proximal in terms of their ability to cover small areas, large areas. That's what I refer here to spatial coverage versus the level of detail in the data. That's the coarse resolution and the fine resolution. So you can see here in space, we can cover very large area, but with very coarse resolution. Proximal sensing systems, we have very high level of detail, very fine resolution, but we can do small area coverage with these systems. So if you look into this graph here and you say, where do we want to be? We would like to be in this particular region. What does that mean? It means that we would like to have the ability to generate digital twins that cover large area and at the same time it has fine resolution or high level of detail. So the question, given this physical characteristics of the sensing sensors and platforms, and our objective, which is having this fine resolution at a scale, how can we do that? So you can do that by a couple of ways, actually. So one of them is that if you look into these, for example, proximal sensing and near proximal, the UEVs, the wearable systems, or even your smartphones. So by having actually lower cost units that instead of deploying one or two, you deploy hundreds and even thousands of these units, you can really do scalable data acquisition, especially if you rely on crowdsourcing or having this um, data collection by lots of participants. And by using AI tools, then you can achieve this. But having said that, that's still not really the best way to do the fine resolution coverage for large areas. So the best way, and this is really our research long-term goal, is that basically you fuse data from all these sensing modalities and you rely on advanced AI data analytics tools to allow for fine resolution digital twinning while covering large areas. So now I will just give you some examples how you can use data from these sensing systems and modalities for different applications. So here I'm not really going to go through the detail of all this shape, but I'd say that, for example, if you are dealing with transportation, so one of the targets we are dealing with is that how can we make the digital twinning general enough that it can handle different environments or different application domains. And the way we look at this is that there are usually five components that you have to uh, uh, address in order to reach this digital twinning capabilities. So you have to select the appropriate sensors and platforms for your application. You have to do the integration of these sensors. The system calibration is extremely important. The georeferencing and the 3D reconstruction, that's also important. By doing the geometric calibration and the georeferencing, then you can ensure the collected data from different platforms at different times will be properly located. Then you have the data analytics tool that give you the information that you need for decision making and communicating this information to the end user through a proper or effective visualization technique is very important. So you can see when we go from transportation to precision agriculture to forestry to coastal environments, or even non-destructive archaeology, this is just an example, you can see that the components or the elements of this digital twinning paradigm are quite similar. So that's one of the key things, that how you can have uh, a unified digital twinning mechanism or engine that can handle different application domains. And I would just take the next half an hour or maybe 20 minutes to talk about some of these tools in different applications. So I'll talk about transportation resilience, so how we can use digital twinning technologies enabled by AI to provide information for decision making to improve the resilience of transportation corridors. So when we talk about transportation resilience, we have to make sure that our road network operate and can handle any disruptions from different activities, whether they are man-made activities, for example, construction zones, or even natural events like flooding, for example, or landslides. And by having dynamic digital twins of the transportation infrastructure, we can ensure the resilience or the successful operation of the road network. So just to give you an information, what kind of information decision making is looking for a transportation network. So for example, the geometry of the road, for example, including the lane widths, is very important. The road surface conditions, the pothole mapping is quite important. Drainage networks along the road is very important because whenever you have flooding events, you have to make sure that the water is properly drained. uh, uh, Infrastructure, like for example, monitoring the bridges or the retaining wall, which what you see here in the middle. Being able to quickly document crash scene, that's very important. Maintaining the infrastructure that basically needed for continuous operation of the road network is very important. And just to give you an example, this is in North America. Whenever you have snowstorms, you have to spread salt on the road surface in order to make sure that basically you don't have icy roads. And the detection of lane marking reflectivity is very important. So right now, as we get more into use of autonomous vehicles, they rely on lane markings to drive the car within the lane. And just to give you an idea how the some of these conditions evaluate the resilience of the road network performance. So if you look at this one here, this figure says actually what is the impact of the lane widths and the presence of trucks along the road and the presence of work zones will impact the capacity of the road or the lane to pass certain volume of vehicles. So this is usually measured by vehicle per hour per lane. So you can see here, if we have 12 feet lanes and no work zones, and we have large shoulders and there are no trucks, a single lane can pass close to 2,400 vehicles per hour per lane. When we come to 12 feet lanes, but coupled with work zones, and you have 34% of trucks along the road, your vehicle per hour per lane will drop from 2,400 to almost 1,200 vehicles per hour per lane. And then if you have 9 feet lanes with work zones, and again, 34% of the traffic is trucks, you can see that the vehicle capacity will reduce to almost 1,000 vehicles per hour per lane. So that's why dynamic digital twin allows us to identify the road surface conditions and the lane widths, for example, and that can give the decision makers an idea about like the ability of the road network to more or less have a non-obstructed traffic flow. So just to give you an example, this is an example in a work zone. You can see here that the lane width is 9.9 feet. You have very narrow shoulder. Next to the shoulder, you have this concrete barrier. So in this case, by knowing this situation, you would know that the vehicle capacity, sorry, the lane capacity in terms of vehicle per hour per lane is extremely diminished. So just going to this framework again, you can really build a digital twinning mechanism that use different data from mobile mapping systems to give us accurate documentation of the road network. So just I give you some examples using these systems which we have at Purdue, the Purdue wheel-based mobile mapping system, high accuracy and ultra high accuracy. So for example, on this particular systems, we have two backward-looking camera. These are the type of imagery collected by the system. This system here, the high accuracy system, we have three cameras. We have front left camera, front right camera, and rear camera. And these are examples of the images captured by these mobile mapping systems. And we have also LiDAR systems on board these platforms. So this is an example of the point cloud data captured by the system. So hopefully the video is streaming okay. So what you see here on the right, you have the point cloud data colored by height. So blue means it's low and red is high. And then you can see here the same data colored by intensity. And one of the important characteristics of LiDAR data when it records the intensity, you can see the lane markings are well defined. You can see the pavement and you can see get more information about the reflective characteristics of the road. So what we really need to do is just would like to take the imagery or the LiDAR, would like to do semantic segmentation or use actually deep learning or AI tools to identify the nature of the objects we can see in the imagery or LiDAR. And I will give you just a couple of examples of AI tools that can be used to do that. So for example, uh, when you deal with imagery, we would like to, for every pixel or for every region that corresponds to an object, would like to give it a semantic or class label. So one of these tools we can use, for example, the segment anything model. So this is a transformer-based neural network that takes an image and partition the image into regions, and those regions they have some common characteristics. You can augment this segment anything model with another network, for example, CLIP, which is a contrastive language image pre-training, to give semantic meaning or semantic label for each one of these regions, whether they are cars, roads, sidewalks, and so forth. So this is just an example of running the semantic segment anything model on some of the images. You can see it identifies the roads, it identifies the trucks, it identifies the sky. But you can see sometimes it makes, because it's a very, very large model. So you can see here on like these barriers, it classifies them as walls. So you can more or less agree or disagree. Is this really considered as a wall or not? So sometimes because it's not really trained particularly for railroad network, sometimes it gives you, I would say, strange labels like walls or buildings along the road or sidewalks sometimes. So this is an example of the right camera for this system here. And this is just another example from the front camera, from the left camera and the right camera. And this is again the high accuracy unit that has front, left, front, right, rear camera. And this is again the left camera, right camera, and the rear camera. So you can see here that we have very good tools. For example, this semantic segment anything model effectively identify the object boundaries and gives them labels. But sometimes you have very strange labels. So for example, if you look at this area here, it says that this is a sidewalk, which is just in the middle of the road. So like, I mean, whatever AI tool, you have to expect that there are some artifacts there that you have to clean. You can do something similar with the LiDAR point cloud data. So, for example, the super point graph algorithm in the deep neural network, it takes the LiDAR point cloud data, it does some geometric partitioning into homogeneous areas, and then it does super point graph to relate these homogeneous areas, and then it has deep neural network to do the semantic segmentation. There is the RAND-LANet is another architecture that takes point cloud data and can do semantic segmentation. We have transformer-based neural networks, for example, superpoint transformer that does the same job. So the key actually here is that you can use these to take the point cloud data and do semantic segmentation. So again, whether you do the AI tools, apply them on the LiDAR data or in the imagery data, you expect artifacts. And one of the key options here is that if you do a fusion between the AI tool output on the LiDAR and the image data, you can improve the semantic segmentation characteristics of the data. So this is just one of the things here. We do late fusion of the outcome from the semantic segmentation of the image data and the LiDAR data to fix the artifacts. So for example, if you look into this image segmentation here, like you see the semantic segment anything that says this is a road, and then it says that the barrier here is a wall. So basically, by fusing this with LiDAR, we can relabel the road into man-made terrain. And then, for example, the wall, we can assign like a hardscape. And the same thing could be for bridge elements. So the most important thing here that you have a rich amount of data, could be point cloud and imagery. And if you really do semantic segmentation and fusing the semantic segmentation results from the imagery and LiDAR, you will have better ability to create more reliable digital twin. So just I will have this video and I hope that the streaming is smooth somehow. So we see here on the top, we have the point cloud data colored by height, colored by intensity. And this is one of the pre-processing elements is that you take the data and you separate bare earth from above ground point cloud. That's what you see at the bottom. And you can take this information and you can do the semantic segmentation. And this is just an example of the point cloud data, but now we have them here colored by the semantics classes. And these are just some examples of the semantic classes. So I'll jump again to the next application domain, and I'm trying to show here that you can have the same almost approach for the digital twinning of a forest environment. And you will see lots of similarities between what we have done with transportation, but now applied to forest or trees in general. So again, forest resilience is very, very important. Again, we would like to make sure that the forest ecosystem can withstand and regenerate after disturbances, whether it's a forest fire, whether it's flood or landslide. We would like to maintain the ecosystem services, for example, the ability of carbon sequestration, the ability to provide habitat to wildlife, and would like to make sure that this is aided by AI-enabled decision making. So digital twins will allow us to do that. And just to give you an example, for forest fire. So if you are talking about what are the resilience factors or the factors that will impact the severity and the spread of the fire, we have different categories here. These require like the canopy, the bulk density, the fuel load, the canopy height, the canopy base height, understory, the debris, the continuity of the fuel load in the horizontal and vertical domain, the overstory density, the overstory type, whether it's hardwood or coniferous, and the understory characteristics as well. So this is kind of information that we would like to have in our digital twin. So again, it's the same components of the digital twinning engine that we had in transportation. And now I'd just like to give you some idea about the different systems in terms of the type of data we collect. So here, this is a forest stand, and I'm just selecting one profile here, and we're looking at point cloud data. So this is captured by airborne. In the US, we have what we call 3D elevation program. That's basically we have a statewide or like a US coverage, wide coverage of the LiDAR. So this is, for example, collected in 2018. So you can see this profile here. You see the ground, and this is the points we captured on the canopy of the tree. So this is coverage here is roughly point density is 6 to 8 points per square meter. This is the same profile, but now it's captured by a Geiger mode LiDAR data from an airborne platform. That's 3 years after, so the 3D data in 2018. This is in 2021, and this is collected in September, which is leaf-on conditions. So you can see that we have some points along the ground and some points above the ground, so you can see the canopy here. This is the same system, but now it's capturing data under leaf off conditions. So it's December 21. So you can see with the leaf off conditions, we have better coverage of the ground. You have better representation of the canopy. If you collect the data from a UEV system, this is in August 23. So this is basically during the leaf on condition, you can see more details about the ground and more details about the canopy and the tree. And then if you have the wearable backpack system, this is basically the level of detail. So what I'm trying to say here actually is different sensors, different platform will give us different resolution. And we have data here from 2018 all the way to 2023. So data sets gives you some level of information, and you have to ensure that this data set is well aligned. So here we are showing the if you do proper system calibration and georeferencing, you see that the 3 digital elevation program in 2018 is well aligned with the backpack data which is captured in 2023. So then you can see actually what happens to the tree grows, which trees have been removed, the variation in the topography, and so forth. Also, you can fuse the imagery and the LiDAR data. So, for example, this is a point cloud data of some of the trees. This is a collected imagery, and you can do actually for the point cloud data, you can use it for the geometry information. You can use the imagery to get bark images that allows us to do species identification. It gives you some information about the forest health. So again, the multimodal integration of the point cloud and the imagery allows you to come up with more complete information about your forest stand, and that's one of the essential needs for a complete or comprehensive digital twin. So without getting into high level of detail, you can have a pipeline that takes the point cloud data, gives you lots of information. For example, like the metrics we need for fire spread modeling in a forest stand. So it's just an example here. This is one of the stands here. We had the mobile pack unit. We can take the point cloud data using AI tools. We can divide them into above story or overstory and understory. That's very important for fire spread modeling. We can do individual tree segmentation. We have the diameter at breast height of the trees, and the height of the tree. So you have these the dBH in inches, the height in feet, and then you have some metrics that gives you the ability to detect individual trees. And you can see here that the precision recall and F1 score are almost 100%. You can see that the missing trees are mainly just because of problems in the reference data, not really in the actual data analytics. We take the trees, we can segment them into groups with a dpH less than 12 inch, diameter at breast height between 12 and 20 inch, and diameter at breast height more than 20 inch. You can do the same thing into categories based on the height. So you can even look into the individual trees, and then you can come up with the merchantable trunk volume estimation. So you have all this information captured by quickly collected data using the mobile mapping system. So I'll just conclude with just some examples of using the mobile mapping to map urban trees, actually, or trees in an urban environment. So this is the mobile mapping system we developed, the mobile pack or bike pack system. This is how we collect the data. This is an example how we drive the system in the campus. So this is just imagery of during the data acquisition. And I hope that the video streaming is going well at your end. And this is the point cloud data captured in the campus. We have very, very fine resolution, very high level of detail. The point cloud data here is colored by height. Blue is low elevation, yellow and red, that's high elevation. And then now you will switch from the coloring the point by height into coloring the point by intensity. And that shows us actually the different reflectivity. So you can see here the sidewalks, they have different reflectivity from the grass. Even the tree trunks and the foliage, they have different um, reflective characteristics. So this information that allows us to do a more semantic segmentation. You can see here the buildings, the lane markings along the road. They are very well defined in this intensity data. And now I'm switching back to the uh, coloring the point cloud by the height or the elevation. So you can take this point cloud data, you can apply the semantic segmentation, something similar to what we have done with the road network data, and you will have this product. So again, this is the point cloud data colored by elevation. This is the point cloud data now colored by the semantic segmentation. So this is ground, vegetation, building, and others. So I'll just jump to like this example here. This is basically the classes here. You have ground and brown, vehicles in magenta, and then the pole-like features are in gray, and then the vegetation. And for the vegetation here, we have detected trees. You can see the height of every tree in feet. So this is very quickly using the geometric calibration, the georeferencing, the application of AI tools to do the semantic segmentation. Just to give you another example, so this is one of the trees. You can have the coordinates, the species of the tree, the height of the tree, the diameter at breast height. And this is just another example where here I will just show you some small examples how much level of detail you can get in the data. So we look into here some of the data where we have the trees, we have the buildings, we have the light poles. So you can detect all this information. For example, here by looking at the distribution of the light poles, how well they interact with the vegetation, you can see are the light poles actually giving enough light to more or less make the sidewalks clear at night or not. So these are the main applications that basically by understanding what you have in your scene, you can make the proper decision to ensure the functionality of the different infrastructure elements. So here, for example, we are looking at the interaction of the trees and the power lines to make sure again that we don't have interference between the trees and the power lines. So to conclude, what I'm trying to say here is that what we are in is basically using geospatial data for digital twinning, and the whole idea is to go from data to information to knowledge. And these are the things basically you have to decide, understand the application needs, decide what is the system you will use, and then you do this AI tools and data analytics and visualization to see whether you can make the right decision or not. And sometimes you have to really say, okay, what do I need to modify in my data acquisition systems, data processing tools to increase the effectiveness of the digital twin and the decision-making process. So my last slide, I'd like to reiterate again that modern mobile mapping systems coupled with advanced data analytics tools allow us to have a digital twin that can improve the resilience of our infrastructure elements. And again, by doing proper fusion of all these systems using AI tools, we can really ensure having very high level of detail at large area towers. So this is just, I would like to acknowledge the funding support we received and thank you for